Hi, I am Shivji, and with me I have Sachidanand. We will talk about unified data management with ClickHouse and Postgres. So, I am a software engineer and a regular speaker across open source conferences and meetups. Love distributed systems and open source. Here are a few databases and streaming technologies that I have been a contributor in and look forward to sort of growing that list. Sachin works with me, and together we sort of go around trying a lot of different technologies, use cases. He is also a regular platform engineer who spends most of his time around analytics databases and meeting like minded people across open source conferences, presenting as well as attending. What we present here is our own opinion, and we are not representing our employer. So, what we will present here today is basically broken down into three parts. One, we paint the picture around the problem statement. Then we tell you the challenges that you can have, and then we propose a thought experiment where we would love to listen in on your feedback. The world today is producing huge amounts of data, and there are also over 1,000 databases. So you find it really difficult to map and may end up with more databases than you would ideally need. Data size across the last decade has grown exponentially. So from 2010 to 24, it has grown around 76 times. Different kinds of data are being generated. For instance, from text, we move to image and audio and now video, and different query patterns in your applications require that we have different kinds of databases optimized for certain kind of data and query. You have row-oriented databases, you have column-oriented ones, you have document-based ones, then there is graph data to model relationships. And with AI now, vector databases are also very popular. The use cases are also evolving. So you have transactions for 3 decades. That's the old guy in the room. Then you have a lot of joint queries within a database across databases that you have to run. And there are databases like, or query engines like Presto slash Trino or Athena that help you with those kinds of things. You have use cases around filtering data, window functions. Do you want to do batch or real time? You want to slice and dice queries, aggregating on different variants. Do you need lossy with a lot of performance, or do you need absolutely lossless architecture? How badly do you want to optimize for cost, which you should in any place, I would think. Availability is important as well. And in addition to this, you have a lot of other concerns around, there's a lot of hype around AI today, and you don't want to lose any data. But how do you store it? How do you make sure that it does not hurt your pocket? You also need to make sure it's absolutely secure. And this is the proof of the pudding, like I said earlier, saying, across the last 1.5 decades, the amount of data has grown in huge numbers. Again, like I said, throwing some more color on it, you have transactional databases like MySQL, Oracle, SQL Server. You have analytics databases, a bunch of them. You have time series. It could be metrics or other use cases. You have a bunch of options there. Then there are vector databases, databases for logging. So you basically see at least around 10 to 15 odd databases, and you could be probably running at least 6 to 8 of them if you are a large enterprise. But the whole list actually is around more than 1,000. You can check the details on dvdb.io. These folks have done a great job in documenting details of all the different kinds of databases. So there are different ways for an enterprise to run these databases. If the DBaaS model works for you, you can just sort of take a subscription and use that database. When you start with smaller enterprise and stuff, this is generally okay. Or if you are a larger enterprise and you have a great partnership, that works as well. But the most challenging parts I have found with these is they can be very costly at scale. You could get trapped into vendor lock-in, or at times you want certain kinds of flexibility that's not supported because you're running in a tight environment. But if you want to run open source data yourselves, you will have a lot of flexibility, but you will need specialized expertise as well, maybe a dedicated platform team for configuration updates, for resilience, legal and compliances. And the large enterprises actually have to also make sure that they are offering high availability. They are load balancing across nodes. So every inch of the resource can be used the maximum. You don't want to throw away resources that are just lying. It costs and hurts your business. On a deeper level, around compliance and security, there is GDPR, HIPAA, and other kinds that require you to do certain things. For instance, you would want to have region specific storage. You would have to encrypt, authenticate, authorize. Reliability and uptime requires you to set up replication, regular backups, disaster recovery, business continuity planning. Performance requires you to, as the data and access patterns evolve, set up right load balancing, caching, query tuning. And then all of these come from your own monitoring and alerting, where you know that, what, I'm going a bit off, and then you go back and fix these things. And then there is obviously resource and cost management. So you are running with optimal amount of dollars, balancing it against flexibility of an on-prem or the ease of use of cloud. You basically see that there are a lot of operational complexity that come with managing a database across your products, and you probably need a central platform team. Now, if you just come to one database, as you scale, you will end up making multiple instances of the database in one cluster or maybe even multiple clusters. But distributed system is hard. While you want your tech to evolve or keep scaling seamlessly, or technically called it auto scale, it is a difficult system to manage. So distributed system requires you to coordinate, manage consistency, fault tolerance, which are all hard to achieve. Going a bit more deeper, you need to care about leader election, ensure consistency is just right for you. You need to go ahead updating your infrastructure on which these databases are deployed. These database will have newer versions, and you have to go across this maybe in a rolling update fashion. There'll be migrations at times. If you're running so many databases, you'll have to move data around, or sometimes you don't want to just change databases. You don't want to have any downtime at all. Plus, the cost has to be minimum, and there should be no data loss. Now, if that is true about one database, which requires so much complexity, imagine the complexity when you have more databases than you require. So if you can get done with one, great. Two, more complexity. If you have five, you have a lot of complexity. And trust me, I've seen people using a database for log management, another database for analytics. Maybe you have a Kafka thrown in there, you have a Postgres or a MySQL, something like that. So there is a lot of complexity. They've spread across different databases. So you ideally want to reduce the number of moving parts always in architecture. And databases are really hard. So you really want to make sure that the number of databases is absolutely as least as you can afford. And you save around cost, you concentrate your expertise, you don't move around data, and you want to have really resilient stack, which you don't have to change so much. And here is a couple of databases that we would propose. One is Postgres, that we absolutely love, and I think most people around the world love, which shows up in the DB engine rankings, where Postgres has been featuring often, and for good reasons, because it's as open a community as you get, mature, robust, and highly extensible database, a lot of data types and use cases, a strong community and support, and proven reliability for transactions across 3 decades, while it is also growing in other directions with extensions. Case in point being Hydra, which is column-based storage around Postgres, built as an extension. PG-DuckDB is basically within the extension you run DuckDB for analytics. ParadeDB is a newer database on the horizon, which is again built as an Postgres extension for search and analytics. Conventionally, Elasticsearch would do this.
As Shiv rightly pointed out, for transactional workloads, Postgres works really well. And with all the extensions that are mentioned earlier, we can also make use of Postgres in some of the analytics cases. But as our data grows into huge amount, then Postgres is still not mature enough to handle that. So that's where the ClickHouse comes in. So ClickHouse is a pure column-oriented database. As we know, Postgres stores data in row-oriented mode. So ClickHouse combines all the columns and stores it in one place in disk. So that's where the column-oriented store is. And it has high compression ratios, which will definitely increase our performance. And there are cases like time series. For that, ClickHouse has recently added dedicated time series engine. In cases like log, for this case, as we know, like Elasticsearch is doing good for a long amount of time. But now ClickHouse can also perform well with all its compressions, codecs applied to all the right data types. So all these cases are covered by ClickHouse really well. So there are also some cons, like if you have some workload which is like where update and delete are frequent. So in those cases, ClickHouse will not perform so well. So as we can see, for ClickHouse, there are also not only us, but companies like Cloudflare, Uber, Vimeo, and Lyft. So these companies also, I have added few of the blogs where they have used ClickHouse for different kind of use cases. Also, we can find hundreds of them in the internet. So together, what we are proposing here is Postgres and ClickHouse. Wherever Postgres is lacking, ClickHouse can pitch in, and wherever ClickHouse is lagging, Postgres will pitch in. So together they are like perform a amazing duo, like Batman and Robin. So whenever we are talking about handling large amounts of data, we have high speed analytics and heavy workloads. So ClickHouse is very fast in those cases. But together with Postgres, we can handle all the transactional workloads as well, which is the modern data requirements. So there is a wide range of ecosystem available for, let's say, streaming data, messaging data, where ClickHouse and Postgres both have wide range of connectors. So now we are here talking about movement of data between Postgres and ClickHouse themselves. So this use case will occur when some of our data is lying on Postgres and some of our data is lying in ClickHouse. So we have mentioned like three ways here, but there are a lot more than this as well. So first way is Postgres SQL table engine. I will come to this in the next slides. I will show a quick demo. So second is Alternity ClickHouse connector. So Alternity ClickHouse connector is used whenever we want to replicate in real time MySQL and Postgres data to ClickHouse for analytics use case. So this is like a single executable, so it can be deployed in on-prem, cloud, or Kubernetes. Support is very well. So it has auto schema conversion, some of these pros I'm mentioning. And as we know, for column-oriented databases, if we insert a single row, then the performance will be bad. So in those cases, Alternate ClickHouse connectors comes with out-of-the-box batch insert support. So one more way is ClickHouse FDW, that is foreign data wrappers. So here I am mentioning Supabase. So Supabase is a company which provides alternative to Firebase, which uses Postgres as its backend. So we can directly query to ClickHouse and get data into Supabase using the ClickHouse foreign data wrappers. So this unlocks wide range of use cases. Like you want to provide your customer with single query interface for transactional workload and analytical application. So customer will issue a single OLTP query, and Supabase will internally go to ClickHouse and get the data back and give the results back to the customer. So this way it will help. And also we can do joins easily from data which is lying in Postgres and ClickHouse. So for ClickHouse FDW small demo, a 2-minute demo is in this link where it mentions all this, how it is done. So it uses parameterized views very well to achieve this. So we can refer to the quick demo which is provided in this link. So going ahead, we have heard already so many use cases and success stories from e-commerce platforms, financial services, and IoT. So IoT is recently booming up due to there are a lot of end user devices, sensing devices where ClickHouse acts as a data warehouse, and we are getting large volume of data to do the IoT data processing. So in these cases, we can combine Postgres and ClickHouse data movement to meet both end of our needs. So here I am giving just a quick example of Postgres SQL table engine. So I have in Postgres, I have a table called leads, which is containing ID integer and name column, which is basically varchar, that is string. So in ClickHouse, I have created a corresponding table, which I've named just PSQL underscore table. So this table has engine Postgres SQL, where I have provided all the Postgres details like host port, then database name is test, table name is leads, and username and password. So when we give all these details and create a corresponding table in ClickHouse, as we can see in the screenshot, in the step 1, we have data lying in Postgres. So in the step 2, we have created the corresponding table, which is showing all the data here as well in the next query if you select start from PSQL underscore table. In the step 3, we inserted one more row. And in the step 4, you can see that row also appeared in Postgres. So this is like one quick example of how it is easily we can move data around between ClickHouse and Postgres. So one more heavily used use case in the industry is change data capture. So for CDC integration, ClickHouse has recently acquired PeerDB. So this will also boost the data movement between these two databases. So PeerDB, what it does is it takes a bunch of sources and a bunch of targets. So and it replicates the data near real time. So in the sources, we can provide Postgres, AWS RDS, or GCP, Azure Postgres. Then we can provide Supabase or NeonDB. So those things we can provide, and it will take the data. And in the targets, we can provide ClickHouse and other targets also. But recently, it is focusing more on ClickHouse. So the data will be captured and transferred into ClickHouse with minimal lag, and that is configurable. We can configure 10 seconds or 1 minute depending on our workload, and it will easily transfer that data. So it has also out of the box like features like, let's say, row level transformation that can mask your personal data in the real time. So with this, we can have a ecosystem where we can move data in bidirectional manner between these two databases. Yeah, with this, I will just hand it over to Siv.
So I'll quickly highlight the picture we wanted to paint so it's not left in the woods. So the point we're trying to make here is that if you have an enterprise use case with a lot of databases and stuff, which we've seen out there in the world, you need to reduce the number of databases because running every database with a lot of expertise is a much better option. You probably build a platform team, and if you can get done with a Postgres and ClickHouse, and maybe in your case another couple of databases, which could be slightly different from these. But in our mind, this should work really well for most use cases. Now, if we again go back to the same thing that we had talked earlier, we have transactional data, analytics data, metrics, vector, logging, whatnot. You can still get done in the way that we propose here, saying Postgres for transactions. If you have a slightly small amount of data for analytics, you can use Postgres extensions. Or if you have a huge amount of data to crunch around, you can use ClickHouse. For time series, you can again use a timescale DB, which is a Postgres extension, or you can use a ClickHouse. It will require you to put some effort, but with a central team helping the product engineers across products, it works wonderfully well. For vector DB, you can use PG Vector. This will solve 80% of your use cases at least. If not, we would generally recommend that you go around and make certain open source contributions to make it work for you. That's how the community is going to grow. And for logging, we found that we've spent a lot of time figure out that with some novel architecture decisions on how you spread across your data, rows, cortex, compression, etc., logging is really neatly done with ClickHouse as well. So that is all we have.